Okay, hello everyone. I am Utkarsh Gupta and I am from IIT BHU CSE. I'm in second year. I'm going to third year right now. So today I'm going to take this session, and the topic is range query data structures. And I'll be covering all the basics and fundamentals. So as such, there are no prerequisites. If you have basic knowledge about programming and time complexities, then it's fine. You can attend this session. And I won't be covering any implementation detail because it is already available on the internet. And I believe that if you have a good knowledge of the theory of the data structure, then it shouldn't be hard to implement. So I'll be trying to make the theory very clear. That's why I won't be discussing any implementation detail. So let's begin. And so first of all, to see why these kinds of data structures are necessary, let's discuss a question. So I'll start with the question. Let's say you are given an array, and along with the array you are given a range. For example, here this is the range, and what you have to do is you have to print the sum of all the elements inside that range. So this is actually very easy, and what you can do is you can just one by one add all of these elements, and you'll get the sum. But if we change the question a little, let's say instead of giving a single range, I give you q queries. So I have given you q queries, and in each query I give you a different range. For example, let's say I give you this range in one query, in another query I give you this range, and you have to answer all of these queries, and you have to do it efficiently so you don't exceed the time limit. So in this case, we'll be using a very commonly known data structure, or it's actually a technique, and many of you already know about it. But there are some very obvious things about it that you must have never cared to notice. So I'll be discussing that as well. So it will be helpful even if you know about it already. Let me just go to a new page. Yeah. Okay. So let's say we have an array. Okay. And what I want to do here is I want to answer each such query in constant time. For example, if I'm given this range, I want to be able to print the sum of these elements in constant time. So what I'll do is I'll do some pre-processing. In fact, I'll make another array corresponding to this array. And in this array, I will store the cumulative sum of the above array, or the prefix sum of the above array. So what this means is, this means that at each element, I'll store the sum of all the elements in the above array which have index less or equal to that index. For example, here, I'll just copy this 2 here. So this is 2. Then I'll add these both elements and write it here. So it's 7. Similarly, I'll put 14 here, then 17, 18, and 23. So what is the advantage of this? The advantage is that now if I want to answer any query, what I'll do is, let's say I have this query range. Now I want the sum of these elements in constant time. So I'll use this array in such a way that I know that this element contains the sum of all of these elements. And I also know that this element contains the sum of these elements. So I can just subtract 7 from 18 and I'll get the required answer. So I hope this technique is known to most of you. But now I will cover some other features about this prefix sum, which might not be known to all of you. So let's talk about some of the details. So first of all, the pre-computation cost is O of n. So you can perform the entire pre-computation, and by pre-computation I mean this prefix sum array. You can perform this pre-computation in linear time, and for each query you have to each query can be performed in just constant time. So these are the two main features. Apart from that, let's talk about the speciality of the operation. What I mean is, in the question we had the sum. Let's say we had some other operation, like instead of sum, let's say I had okay. So in the question, instead of sum, I had some other operation, let's say multiplication or XOR or AND or something like that. So could I have used this technique for that operation? So let's talk about some specialities of the operation. So first of all, to use prefix sum, the operation must be invertible. So this is very necessary. So like it can be used for sum because we can easily get the inverse of the addition operation, and that is the subtraction operation. It can be used for XOR as well, because in XOR the inverse is the element itself. But we can't use it for things like max or min or GCD, because these operations are not invertible. Like if you know what I mean to say is, if you know the maximum of this range and you know the maximum of this range, you can't use these two to just get the maximum of the middle range. So this operation is not invertible. So the operation must be invertible if you want to use prefix sum. So let's talk about some other features. So one important feature is you cannot perform updates if you are using prefix sum. What it means is, in between the queries, you can't just change an element to some other element and hope that this will still work. Because in the worst case, if you change the first element, what will happen is that you have to update all of these elements. So the update operation will cost you ON or linear time, and which is bad. So updates are not possible with prefix sum. Now another important property is, which most of you must have never thought about because it's so obvious. So this property is called commutativity. Okay, so we all know that commutativity means that A dot B equal to B dot A for any operation, and we know that addition is commutative. But the thing is, for the prefix sum technique to work, we don't need commutativity. Like even if the operation is not commutative, this technique will still work. So what this means is, if we didn't have an array with the numbers and we wanted the sum, instead of that, if we had some non-singular matrices, I'm saying non-singular because non-singular matrices are invertible. So if we had some non-singular square matrices and a lot of non-singular square matrices, and we wanted the product in a range, we could have used the prefix sum technique, because commutativity is not required, because we're never changing the order of the elements, like we're processing them from left to right. So that's why commutativity is not required. So there isn't much more to learn about prefix sum. I think I've covered almost everything. And I won't be talking about questions related to this because this is a very basic technique. But let's think of something better, because there are a lot of disadvantages with this technique, and I want to remove some of those. So I think the biggest disadvantage is that it requires the operation to be invertible. And I don't like that, because there are a lot of operations which are not invertible, but they are important in operations like minimum, maximum, GCD. So these operations are important, but these are not invertible. So I think I need another data structure or another technique for these. So let's try something else. Let's try making blocks. So by blocks, I mean that let's say I have an array. Okay, so this is my array. I'm not filling in the elements because it's not required. Let's say I choose a block size. I'm not choosing a constant size. Let's just call it capital B. So I've chosen a block size capital B, and I'll just store the sum of let's say B consecutive elements. Let me make another element here. Yeah. So I will store the sum of every B consecutive elements, and this B is not constant. So why am I doing this? So I'm doing this because let's say I have a query, and the query is something like this. Let's say this blue range is the query. So what to do? So it is obvious that some blocks will lie entirely within this range. Let's say this block and this block. These lie entirely within the range, and some blocks will lie partially within the range, like this block. And one thing we can notice is that at most two blocks will lie partially within the range. All the other blocks will either lie completely within the range or they will lie completely outside it. So what we can do here is that whenever I have a query, I'll take all of the blocks that are lying completely within the range, and I'll take their sum. Let's say these two blocks, I'll take their sum, and then I'll add the extra elements like this element. So in this way, I'll get the sum. So let's talk about the time complexity of this. We can say that we can see that the precomputation is obviously in linear time, because we're just pre-calculating it for each block, and it's not costly. But what about the query time? So for the query, as I said, only two blocks will lie partially with the query range. So in both of the blocks, there can't be more than B elements. Okay. So let's say I have around 2B elements at most. But how many blocks can be there? So at most there can be n by B blocks, where n is obviously the length of the array. So what this means is that in O of 2B upon n plus n by B time, I can perform a query. So what size of B should I choose? So if you apply those standard techniques like arithmetic mean is always greater or equal to geometric mean and things like that, you'll realize that the best block size is approximately around square root of n. So this is because when we put b equal to square root n, both of these elements will be approximately equal to square root of n, and each query will work in square root n. So that's why this technique is called square root decomposition, because we're basically breaking the array. So that happened because of some connectivity issues. Anyway, so we call it square root decomposition because we're breaking the array of length n into square root n arrays, each of size square root n. So I'm not going to talk much about this technique. The reason is that this is a very vast technique, and there are like hundreds of ways of applying square root decomposition, and they can be used in many places, and this is just one of them. And this is not very helpful here. Like the next things I'll talk about are much better than square root decomposition for this case. So I think square root decomposition deserves another separate session, and I might do such a session later. But for now, the reason I talked about this was just to show that making blocks is good. So this is an important point. Like it's good to make blocks, and if you look at the time complexity which I discussed earlier, it was around O of B plus n by B. So what you can note here, okay, yeah. So what you can note here is that no matter what the block size is, as far as it's greater than 1 and smaller than n, this is better than doing it naively. So blocks of all sizes are good to a certain extent. So let's just use this idea to see why the next data structure that I'll talk about is good. So I'll just write the heading. Okay, so the next data structure that I'm going to talk about is sparse table. Now, like previously we learned that blocks are good. So I think whoever invented sparse table must have realized at some point that blocks are good, and then he went all crazy about it and said, okay, now I'll make as many blocks as possible. I'll make overlapping blocks. I'll make blocks of different size, and now I'm going to talk about sparse table. So instead of talking about how it's built, first I will talk about how to query with it and what kind of pre-processing is done. After that, I will tell how to build this sparse table. So in sparse table, the pre-computation we do is, let's say I have an array. I'll just fill in some elements. Okay. So in sparse table, what we do is we make a lot of blocks, and these blocks are of different sizes. To be more accurate, what we do is, starting from each element, like from each element, this element, this element, this element, from each of the element, what we do is we form blocks of all powers of 2. Like for example, I started from here. So first of all, I'll make a block of size 1, which is 2 to power 0, and store the sum of this block. So this is obviously the element itself, and it is 3. Then I'll take a block of size 2 and store the sum of that. So that is 2 plus 3 equal to 5. Then I'll make a block of size 4 and store the sum of that, and this is 14. So like no matter how long the array is, I'll keep storing the block sizes, and they will be in powers of 2. So at most, how many blocks will I make? So I'll make for each element, I'll make log n blocks. It's because the size of the block is doubling uh, each time. So actually, it's log n base 2, and it's because if I double a number log n base 2 times, it will be equal to the number, and I cannot have a block greater than that. So what is the advantage of this? Let's say we have already made all of these blocks. So how will we use this to perform a query? So let's see how to use this to perform a query. So actually I'm going to add one more element. Okay. Now let's see the method of answering a query first. Let's say I have a query in this range. Okay. So it's from the index 1 to the index 6. So the length of this range is 6 elements. 6 is the length of this range. Now what I will do is I will write the binary representation of this number, and actually I'm not writing the binary representation. I'm just breaking it into powers of 2. Like 6 is equal to 2 plus 4. Okay. So just like this, we can break any number in powers of 2, and there won't be more than log n distinct numbers in the in this kind of representation. So we broke 6 in 4 and 2. Now what I will do is I'll start from L. L is the point where the query starts. Now what I will do is I'll uh, I'll jump from here, and I will jump as far as possible without going outside the query range. So the biggest jump that I can perform here is of length 4, because if I perform a jump of length 8, I will go outside the range or outside the array. So I'll perform a jump of length 8, and I have already stored the sum of these elements, and I know that the sum is 14. So I have already stored it. After that, I'll move to the next element, and again I'll perform the longest possible jump and add that as well. So in this way, I can solve a query. Okay. So now the question is, what is the time complexity of this method? So the time complexity of answering a query is O of log n. The reason is that we can perform a single jump in just constant time, and we are not performing more than log n jumps, because any number can be broken into powers of 2, and there will be only log n terms in that kind of decomposition. So each query can be performed in O of log n time. So this is slower than prefix sum, but the good thing about this is that we don't need the inverse of any element. We're just taking the range that is included in it. We're not taking anything extra and subtracting from it. So the operation doesn't have to be invertible. So what this means is we can use this sparse table for operations like max, min, GCD, even for non-singular, even for singular matrix multiplication, we can use this. So these are the advantages of a sparse table. Now, as I said, after I explain how the query works, I'll explain how to build such a sparse table. And I'll also talk about in how much time the sparse table can be built. So I have this array. Now I need blocks of all powers of 2 from each element. So at most there are n log n blocks. And if I can compute the value inside each block in constant time, then I can perform the entire pre-computation in just O of n log n time. So let's see how I will do the pre-computation in constant time for each block. So what I will do is I'll start with the smallest power of 2, and the smallest power of 2 is 2 to power 0, which is 1. So at the smallest power of 2, each block is just the element itself. For example, if I have 2 in this element in the array, then this block will just contain 2, and so on. So it was okay. Okay, yeah. So it was pretty easy to just uh, form blocks of size 1. Now I want blocks of size 2. So for blocks of size 2, I just have to add 2 adjacent blocks of size 1. So I'll add this block and this block, and I'll get this block. Similarly, what I can do is I can add this block in this block and I'll get this block. And again, so in this way, I can use the blocks of size 1 to form the blocks of size 2 in constant time. I'll form each block. Now, let's say I have stored all of the blocks of size 2. Now I want blocks of size 4. So for each block of size 4, what I will do is that I will just use the blocks of size 2. For example, let's say I have this and this. So this is 5 and this is 6. Now I want this. So I can just add 5 and 6 and I'll get 11. So in this way, I can use the blocks of 1 power of 2 and I can use all of these blocks to get blocks of higher power of 2. In this way, I can pre-compute each block in just a constant time, and the total number of blocks are less than n log n. So the pre-computation will take n log n. And there are some other ways to perform faster pre-computation, but they are very complicated, so I won't be talking about it, and you'll probably never need it because n log n is fast enough. So anyway, so let's talk about the properties of a sparse table, just like we talked about the properties of the prefix sum. Okay, so first I'll talk about updates. So just like in prefix sum, here also we cannot perform an update. The reason is that if you try to perform an update, you'll have to, like in the worst case, you might have to change all of the blocks. And that will take a lot of time. That will take n log n time, which is too much. So updates cannot be performed. But another property is invertibility. So I've already talked about it. Invertibility is not required in sparse table. So we can use it for operations like max, min, GCD, etc. So no need to talk about it again. Then another property is commutativity. So here also we are not changing the order of elements. We are processing the blocks in a left to right order. So here also commutativity is not required. Okay. So now I'm going to talk about a new type of property, and that is called idempotence. So what idempotence means is that, let's say I have an element A and I have some operation and I perform the operation of A with A, then I get A again. So the operations that follow this property, they are called idempotent operations. Like there are some matrices which follow this property during multiplication. So they are called idempotent matrices. And max is an idempotent operation. For example, max of 4 comma 4 is 4 itself. So there are a lot of operations which are idempotent and some of them are actually very important. For example, GCD is also idempotent. GCD of x comma x is x because x is the common divisor of itself and there cannot be any greater divisor of x than x. So what is the use of idempotence here? So as such, I haven't used idempotence yet, but I'm going to use it now. So let's say I have to perform some idempotent operation on this array, and wait, I'll add one more element. Okay. So let's say I want the maximum. I want the maximum element in this array. So if I use and my query range is the entire array. So if I use the normal sparse table for this operation, what I will do is from here first I will perform a jump of 4. Then from here I'll perform a jump of 2. Then I'll again perform a jump of 1. So in this way it will take log n time, which we have already established. But for idempotent operations, we can actually do it faster. Let's see how. So let's see the biggest jump that we can perform from here. The biggest jump is of 4. Now come to R, the point where the query ends. From here, let's see the point from which the biggest jump ends here. So the biggest jump in this range is 4, and from 1, if we jump till 4, from 1 if we make a jump of 4, we will reach the end of the query. So this cannot be used for operations like addition or XOR or something like that, because what we're doing is we're repeating some of the elements, and that is the problem. But the good thing here is that the operation max is an idempotent operation. So if we're repeating some of the elements, it doesn't matter. So we can repeat some of the elements, and if we perform jumps like this and don't care about the repeating elements, then we can perform one query in just constant time. And that is the main power of a sparse table. We can perform queries in constant times if the operation is idempotent. And it is a good thing because operations like max and min are idempotent. GCD is also idempotent, but yeah, let's talk about GCD as well. So we know that GCD is idempotent, but if we use that along with the sparse table, it's a common misconception in some of the very experienced people that the sparse table will work in a constant time, of one time, because the operation is idempotent. But this is wrong. That's not how it works. The thing is, it is constant time because we are performing the operation on just 2 blocks, and some of the area might overlap. So usually that is why it works in constant time. But that doesn't happen with GCD. And the reason is that if you use some inbuilt function like underscore underscore GCD, or if you calculate the GCD using any method, the GCD itself will work in log of X time, because the GCD is found using Euler algorithm, and that works in logarithmic time. So even if you want the GCD of just 2 elements, it will take logarithmic time. Yeah. So that's why even with a sparse table, you cannot get the range GCD in constant time. It will still work in log of max element in the array. So that is an important thing to note, And a lot of people tend to forget this, and they think that okay, I'm using the sparse table with the idempotent technique, so I can get the GCD in constant time, but that is wrong. So it works in log of max element time. But for other operations like min or max or and or, it will work in constant time. So that is the main power of the sparse table, because if we're getting just log n time complexity for some non-idempotent operation, then there are better methods available, and I'm going to talk about some of those methods later in this video. But for idempotent operations, this is a very good technique. So since sparse table might be new to some of you, I'm going to discuss a question about sparse table, and it is a very nice question. And if you're not watching it live, you're watching the recording, I would suggest you to pause and try to solve it. So let's say I have an array, okay, and I am given q queries. Each query is of the type excuse me, my internet is malfunctioning. Just wait a minute. Okay, so each query is of the type L comma R, where L and R are indices on this array. Let's say one query is this range. Now what you have to do is, I'll just put in some elements in the array. What you have to do is, inside this range, if there is an element that can divide all of the other elements in the range, then the answer of the query is that element. And otherwise, the answer to the query is -1. So what it means is, there should be one element in the range that is a factor of all of the elements in the range. For example, here we have 1. So 1 is a factor of all of these elements, because 1 can divide 5 or 2 or 7, and 1 is present in this range. So the answer is 1. But if we had chosen some other range, for example, if we had chosen, let's say if we had chosen this range. So let's say we had chosen this range. So in this range, what will happen is that um, there is no element that can divide all of these elements. So in this range, the answer to the query will be -1. So we have to solve this question. So how can we process the queries efficiently? Okay. So what we can do here is that we know that if the element is present in the range and it is a factor of all of these elements, then it is obviously the GCD of the range. So if we are in some other range and we take the GCD of this range, and if the GCD is not present, then the answer is -1. So with this knowledge, or with this observation, let's try to solve this question. So we just need the GCD of the range, and that is pretty easy with a sparse table. We can get the GCD of any range in log of max of a time. So we can get the GCD easily, But how will we check whether the GCD is present in this range or not? So there can be some complex methods to do it, but here we don't require them. The reason is that here we have another important observation. If the GCD is present in the range, and if all of the elements are divisible by GCD, then the GCD must be the smallest element in the range, because there cannot be any element that is smaller than the GCD. And basically what I'm saying is the GCD can't be greater than the elements. So if the GCD is present in the range, then the GCD must be the minimum element. So that yields a very beautiful solution to this problem. What we will do is we will form two different sparse tables. So we will make two sparse tables. So one sparse table will store the GCD and the other will store the minimum. And we will use these two sparse table to get to query in a range. And in the end, we will check whether the minimum and the GCD are equal. If they are not equal, then the answer is -1. But if they are equal, then the answer is the result of the query. So this was a nice question. I think I did it a few months ago on Codeforces. So I think that's all I had to talk about sparse table. Now I'm going to start a very interesting data structure, and this is personally my favorite, and most of the times I use this. So this is called segment tree, or in some places it is also called interval tree. So what we do in a segment tree is that, first of all, we write all of the elements of the array. Let's say I have an array with 8 elements, okay. And the operation is addition for now, but segment tree can work for a lot of different type of operations. But let's say I want the sum in a range, and I will write down the initial elements of the array. So I'll just write 8 elements, for example. Okay, so I have 8 elements of the array. So what I will do here is that I will form a tree-like structure on this array. So basically, actually this can also be thought of as making blocks. So let's say I'll form blocks of size 2 and I'll form disjoint blocks. So 8 plus 2 is 10. Then 5 plus 3 is 8. So let's say on this array, I formed blocks of size 2. And when I was talking about square root decomposition, I told you that blocks of all sizes are advantageous. So even if we make just these blocks, it is advantageous to some extent. But why stop here? Why not continue with this process? Like this is another array. I can make blocks of size 2 here as well. So let's do that. So 8 plus 10 is 18. and 16 plus 4 is 20. So again I formed blocks of size 2, and I can do it again. Actually, let me just erase this. So in this way, I formed an entire tree with the given elements of the array. I'll just circle each of the node. So you can see that a binary tree-like structure is formed on the array, and we can use the so okay. So instead of talking about how to use this for queries, first I'll talk about how to build such a structure. So it is easy to build such a structure because whenever we need to store the value in a node, we just have to add two elements. So the information stored in a node can be calculated in constant time, and this can happen only if we have calculated the uh, level below the current level. Then we can do it in constant time. So what I will do is I'll do it in a bottoms up direction. So first I will store the values in the lowest level, which is the array itself. Then I will go one level up, and at this level I'll just store the values just by adding two elements for each node. So in this way I can store the value of each node in constant time. So the time complexity of building this kind of tree structure is the number of nodes in this tree. So how many nodes are here? So what you can see is, if the length of the array is n, then I have n elements at the bottom level. At the level just above that, I have n by 2 elements. At the level above that, I have n by 4 elements, then n by 8, and so on. So it forms a geometric progression, like total number of elements is equal to n plus n by 2 plus n by 4 plus n by 8, and so on. So this is obviously a convergent series, and if you add all of the elements, you'll see that it doesn't exceed 2n. So this way, using a bottoms up approach, we can pre-compute the values of a segment tree in linear time. So okay, let's say we have formed such a segment tree, and it's called segment tree because each node is storing the sum of some segment. For example, I'll write the indices here. So this is the 0th element, this is the first element, second element, third element, fourth, fifth. Okay. So I've written the indices at the bottom level, and these nodes are storing that value. At the higher nodes, I can see that these are storing the sum of a range. For example, this node is storing the sum of 0 to 1. Then this node is storing the sum of 2 to 3, 4 to 5, and so on. Like this one is storing 0 to 3 and 4 to 7. Okay. So each node is storing the sum of a segment or an interval. That's why it's called a segment tree or an interval tree. Okay, so I'll just erase the indices because it didn't leave me any space. So as I said, I won't talk much about implementation, but let's see intuitively how we can use such a segment tree to perform a query. So let's say we are given a query range, and our query range is this circled part. So we want the sum of this range. So there are two easy ways, and most of the times, so I'll tell what the two ways are. One way is going from the bottom to the top, and the other way is from going from the top to the bottom. So usually people use the top to bottom approach, because usually people use the top to bottom approach because it is easier to implement, and there are some other advantages as well. But for now, I'm going to tell the bottom to top approach, because the bottom to top approach is easy to explain and understand. And if you are doing it manually, it is easier to implement as well. But on computer, I think the top to bottom approach is easier for most people. But okay, I'm going to start the approach. I'll just change the pen color. So first I will pick the left and the right element. So these are the endpoints of the query. Now what I will do is I'll climb to the root of the tree, starting from these elements. So I go up, then I go higher, and I reach the root. From here also, I will go up to the top. So how many, so at max, how many nodes am I visiting? So at max, the number of nodes that I'm visiting are equal to the height of the tree. And it is pretty obvious that the height of the tree is equal to log n, where n is the size of the array. Because at each level, we're dividing the size of the array by 2. So we cannot do that more than log n times. So obviously the height of the tree is log n. So we won't be considering more than log n nodes for any query. Now what's happening here is that how will we pick which elements we have to add and which we have to skip? So what I will do here is I have two conditions, and I'll add a node to the answer only if both of them satisfy. So the first condition is segment must lie within the query range. Now what this means is if there is some element that is outside the query range, for example this 20, this is not this is not lying completely within the query range, because there are some elements that are outside the query range. So I won't add this element, because if I add this element to the answer, then I'll have something extra, and I don't want anything extra. So this won't be added, this won't be added, this won't be added. Actually, we're not even visiting that, but this and this won't be added. Okay. So what will we add? We will add if parent is outside range. So this is important, because let's see at this 2 here. This 2 is lying within the query range, but its parent is outside the query range, because this 8 is not in the query range. So we must add this 2 to our answer. So we will add this 2 to our answer. And one important thing is that whenever you add some element to the answer, you must move to the left, move to the right if you are at the left end, and you must move to the left if you are at the right end. Okay. So we added 2 to our answer, and then we will move to the right, and now we are here. Then we look at this 9. It is inside the range, but its parent is also inside the range. So we want to add this to the answer. Now we will move upward. So now I'm at these 2 points. So they both lie completely within the query range, and their parents don't lie within the query range. So we will pick both of these. So I'll have 8 plus 16 as this. So that is the answer to this query, and it is 26. So in this way, we can get the answer in a bottoms up method. I think some of you must be having some doubts. You can write those on the live chats, so I can. So if you want me to explain more properly, I can do that. But I'm going to talk about the top to bottom method as well. So let's say I have this segment tree again, and this time I'm making only 4 nodes, because I'm taking the array of size 4 because I don't want it to get very messed up. So let's say now I have this range. So to do it from the top to the bottom, what I will do is I'll start at the root, and I'll visit the root. Okay, so basically what I'm doing is I'm doing it recursively. I have a recursive function, and whenever I'm at a node, there can be at most 3 cases. So the 3 cases are, so the first case is the uh, segment lies outside completely, like it lies completely outside of the, actually it should be completely outside. Okay, so if the for example, see this node, so this lies completely outside the segment. So what I will do is, if any segment lies completely outside the query range, I'll just subtract. I'll just return 0 from here. I'll just say uh, I'll just say that okay, the sum of elements in the query range within this segment is 0, because there are no elements that are overlapping. So another case is completely within. For example, look at this node. This node, the segment is this, and it lies completely within the query range. So if we ever encounter a node in which which lies completely within the query range, what we will do is we'll just return the value written in this. For example, I forgot to write the values. Wait. For example, 3 is written here, so I'll just return 3. So from here from here I returned 0, and from here I returned 3. Also from here I'll return 2, because this lies completely within the range. Like this element has this range, and the query range is this. So from here I returned 3, and from here I returned 2. Now let's look at the third case. The third case is partial overlap. So I'm just going to circle the elements which have a partial overlap with the query range. So this has a partial overlap, and this has a partial overlap. So what should we do whenever we reach an element that has a partial overlap with the query range? So it is kind of easy to see that we just have to we just have to visit the children and add the answer that we received from the children. So what I'll do here is when I'm at this 6, I'll add 2 and like when I'm at this 6, I'll add this 2 and this 0, and I'll return 2 back. So from here I return 2. Also, this element also had partial overlap with the range. So here also I'll return 2, I'll add 3 and 2. So I'll just add both of these elements and I'll return 5, which is the answer to the query. So in this way I can perform the query in a top to bottom fashion. So the thing is, in both of these methods, whether it is top to bottom or bottom to top, in both of these methods, the time complexity is O of log n, which is pretty nice because commutativity is not required, just like previously. Also, commutativity is not required, and the pre-computation is also only On, which is linear time. So that is also good. But the most important feature here is that unlike sparse table and the prefix sum, here we can perform updates as well. So this is very interesting. Let's see how the updates can be performed. Oh, I erased the tree. Wait. So I'll just redraw the tree. Okay. So this is my tree. And now I want to perform some updates. So earlier what used to happen was, in sparse table and prefix sum, what used to happen was, uh, whenever an update was performed, the entire structure used to get broken and we had to rebuild it, and that used to take a lot of time. But here it's not like that. Let's say I want to remove this 5, and instead of that I want to write 9 here. So let's see which of the nodes will change. So I'm just gonna highlight all of the nodes that will change. So obviously this will change. Also this will change. This will change. And this will change. So you can easily see the pattern that only the ancestors of the node will change. And the remaining tree will be intact. Like none of these values need to be changed upon performing an update. So this is a very good thing because the total number of ancestors of any element are equal to the height of the tree, and that is not more than O of log n. So because the height of the tree is log n, we have to update only log n elements. So what we can do is we can change all of these elements, and there, now our tree is perfectly correct, and there is no element that has wrong information. So that's a very good thing about segment tree because Using this, we can perform updates in just O of login time. So that's a good thing about segment tree, that we can perform updates. So these type of updates are called point updates. Now I'll talk about some more rigorous updates, and they are called range updates. And range update can be like performing an operation on an interval. So it can be like, let's say I choose this interval and I say add 6 to all of these elements. So the first thought is, what I can do is I can one by one apply a point update on all of these elements, and replace the element with the value +6. For example, I'll write 8 here, then I'll write 9 here. But this is slow, because let's say we have queue updates. So this entire task will take around queue login time, which is a lot, because if uh, if q is around 10 to power 5, uh, and I mean, actually this is not q login. I mean, let's say the length of the interval is capital L, then it will take L login. So this is a lot, because if we have q such updates, then the total will be QL login, which is bad. So we cannot use the point update method to perform range updates. So we will use something else, and that something is called lazy propagation. So lazy propagation is actually a difficult topic, and if you are hearing about it for the first time, it must be difficult for you to understand. But still, I'll try to give a proper explanation as to how to do it. So let's say, let's take a easier case, not the general case. I'll take an easier case. Let's say that the update range lies, like the update range coincides perfectly with the segment range of an element. For example, let's say my update range is this, and I have to add 6 to all of these elements. So what we can see is that for this node, the update range coincides exactly with the segment range. So in this case, it is easy to perform the update, because I know the width of this range. The width of the range is 2. Width of the range means how many elements are in this range. So we can see that there are 2 elements, so the width of the range is 2. So if I have to add 6 to all of these elements, what I can do is I can just add 12 here. So instead of adding 6 to both of these elements, I just added 12 here, and also all the ancestors will be changed, so I'll add 12 to all of them. So now in the tree, all of the elements are having correct information stored in them, except these two. These two are having wrong information stored in them. So to fix that, what we can do is we can add 6 here from here and then add 6 here. But like that's the point of lazy propagation. It's called lazy propagation because the person who is propagating these updates is lazy. So instead of sending these updates downwards, he'll just store it. Let's say I'll write it with a different color. So he just wrote 6 here. What this means is this person remembers that he has to add 6 to the children, but he has not done it till now, and he will do it only if it's necessary or whenever it is necessary. So now if I have queries in some range that is outside these two elements, like let's say I have this query, then this can be done very easily because because these nodes are never even used. So we don't care if they have the right information or wrong information, because we just need this node for this range. So that's how we can perform queries that lie outside the segment range. And let's talk about the queries which cover the segment range entirely. Let's say I have this range. So the queries in this range can also be solved without going to the children, because if I start in a top-down approach, what I can do is when I reach here, I'll just say that okay, this element lies completely within the range, so I don't need to go downwards. So this kind of query can also be performed without going to the children. But what if the query is like this? Then we will have to move down from here, and now it will cause some issues because the information in this node is outdated, and we need to update this information. So what we will do is, whenever it's needed, like whenever such a query occurs or such a query occurs, what we will do is whenever we reach here, we'll check if there is any remaining lazy value. And if there is some lazy value remaining here, what we will do is, before moving to the children, we will propagate this lazy value downwards. So basically what happens is, if such a query arises, what we will do is, when we reach here, before going to the children, what we will do is we will add 6 to both of these elements. Actually, I'm writing in green. So we'll add 6 here and we'll add 6 here. So in this way, the information can be corrected. So why is this advantageous? Let's see. So first of all, let's talk of a more general case. Let's say the update range doesn't coincide exactly with the segment range. Let's say our update range is something like this. Like we had to add, let's say again, we have to add 6 to all of these elements. Let's say we have to add 6 to all of these elements. So in this more general case, what we can do is we can start in a top to bottom fashion, and we will do everything like we will visit the vertices exactly like we visit in the query. Like we will make the function very similar to the query function. And what we will do is, whenever we reach an element, which should have been considered for query. For example, these three elements. So we know that all of these three elements contain the entire range, which lies within the query range or update range in this case, and their parents do not lie within this range. So what we can do is we can perform the lazy update on all of these nodes, and uh, in fact we don't have to perform a lazy update here because this is already at the bottom level. So we will never need to propagate downwards because there is nothing below it. So what we can do here is that we can just add 6 here, then we can add 12 here, and we can add 12 here because the width of these two elements is 2. And we will store some lazy values. So here I'll store 6 as the lazy, and here also I'll store 6 as lazy. So since I did everything like I do in the query, then it is pretty obvious that this also should work in just login per update, because I'm not doing anything different. I mean the uh, update function is very similar to the query function. I'm visiting the same number of nodes. I'm visiting in them in the same sequence. I'm just doing a different thing. Instead of uh, adding their values, I'm updating their values and storing something in the lazy. So at each node I have a lazy, and in this way I have stored how much lazy value it has, and whenever I'll need it, I'll propagate it downwards. Okay, so that's how I performed one update. Let's say I have another update. Now this update is in this range. Now what will I do? So again I'll let's say in this range I have to add 9. So again I'll do the same thing. I'll call the update function, which works just like the query function. I'll move from the top to bottom, and whenever I reach a node that contains the interval completely, I'll add to it. I'm sorry. I'll add the update value to it multiplied by the width. So here the width is 4, so I'll add 27 here. Then here I'll add okay. So I added 18 and 27 here. But what about the lazy values? So ideally I should have written 9 in the lazy variable because I have to propagate 9 downwards. But this node already has the lazy value and it is 6. So what should I do in such a case? So in such a case, what I will do is I'll add the new lazy value to the old lazy value. So I'll do 9 plus 6. So I'll update the lazy value as well. So in this way, I have 13 as the lazy value, and here the lazy value is 9. So I think it has become very dirty. I'm going to erase everything. So in this way, I can perform the updates lazily, and each update works in O of login time, which is pretty good. And at the same time, the queries also work in O of login time. So that's the advantage of a segment tree. Now there are a lot of different types of segment trees, and I'm not going to talk about those because they are very advanced. Like there is persistence, there is dynamic set tree, and a lot of other things. But in general, I talked only about lazy propagation and queries. So there's one important thing about lazy propagation. So that thing is, let's say a node already has a lazy value, and I'm writing the lazy value with red. Let's say the lazy value is 6. And then its parent sends another update to it, and then I get another lazy value, and I have to add those. So if the update is add on a range, it is very easy to combine two lazy values, and I can just add them to get this value. But if the update is not if the updates are not add on a range, if the updates are more complex, for example, um, like apply this operation on a range. What this means is, if the element is x, convert it into ax plus b, where a and b are given. So for example, if let's say, I mean this is basically a linear function, like 6x plus 5. So if the initial value is like let's say 3, so what I'll do is I'll convert it into 23. Basically, I'll pass x to this linear function, and then I'll perform the update accordingly. So how do I combine two such updates? Let's say I have one update f1 equal to a1x plus b1, and I have another update f2 equal to a2x plus b2. So here combining isn't like just simply adding. Here combining is like making a composite function. For example, f1 dot f2 will be equal to f1 of f2 of x. So in this case, I'll just show how to combine two such updates. For example, one of the update is ax plus b, I mean a1x plus b1, and the other update is a2x plus b2. And I want f1 dot f2. So what I'll do it, instead of x, I'll put in this value. So it will be a1 of a2x plus b2 plus b1, and that will be equal to a1 a2 plus a1 b a1 a2x plus a1 b2 plus b1. Now I can represent this in the original form. I can write it as a3x plus b3, where a3 equal to a1 a2 and b3 equal to a1 b2 plus b1. So that's how I can combine two complicated updates. And there are a lot of other kind of updates, and for each type of update, you have to think of the method to combine those updates. And so you need to be able to implement the combine function for two updates, and this is important. For addition, this is easy because in addition, the combination of two numbers is just the sum of those two numbers. but in other operation it can be harder. So okay, apart from this, let's say you have like you know how to combine two updates, but then you need another function. You need to be able to apply the update. So I like to call this function apply, and this is not a standard nomenclature. That's I mean, like that's my own personal lingo. So what apply means is that, let's say I am at a node. Okay. So if I know that I'm performing, like this is not the root, they can be higher node, but I'm not showing them. Let's say I have to perform an update here, which means I have to perform an update on this entire range. So what I will do is I'll just let's call this node V, and let's call the update U. So I'll just apply U on V. Basically, this function means that I have to apply the update to the node. Like we have to apply U on V. So what is the problem here? The problem here is that if the update is simple, like I said, if the update is add on a range, then it's pretty easy to just apply the update to the node. All we need is the width of the node, or the width of the segment, and we need the value. So we can just multiply the width and the value and add it to the node, and we can store the new correct information. But sometimes it's not easy to store the new correct information in just one operation. For example, let's say that the segment tree returns the sum on a range. Okay. Now the query function is sum on a range. Now I have an update of the form, like replace x with max of x comma y. So now this is a little difficult, because the problem here is that we cannot update the sum in a single operation, because we need to know how many elements in the range are greater than y and how many are smaller than y. So this is very complicated, and in general it is not easy to apply such an update, and there is a very complex way to do this, and I won't be talking about it because it is out of scope of this discussion. But it is called segment tree beats. If you are interested, you can Google it, but it's very difficult. So I think that was all about segment tree, and I don't think if you are new to this topic, you would have understood it properly. So I recommend you should watch it again, and you should also read about segment trees from CP algorithms. So there's this website. I'm going to write the link. So you can learn more about segment trees from this website. It has a lot of CP algorithm. You can learn a lot of things from there. I think a lot of you already know about this, but that's all I had to cover about segment trees in this discussion. Now I'm just going to end, but in the last few minutes I'm going to talk about Fenwick tree. So I'll do this very quickly. And this time I won't go into the basics and fundamentals. The reason is that if you find the code somewhere, if you find the code of a Fenwick tree somewhere, it is very small, and you don't really need to know much about Fenwick tree to be able to implement it, because the code is so small you can just memorize it or write it somewhere. So basically, I'll just tell what it does, and I won't tell how it does it, because that is a little complex. So what it does is that there are basically two operations. One is update and the other is query. So this update operation performs point updates. So basically you can update the value at any point of an array. Let's say I have an array. I form a Fenwick tree on this array. So it supports an operation that I can, let's say 3 is here. So even after the pre-processing, what I can do is I can delete this 3 and write 5 here, and it will still work. But this doesn't update, but this doesn't support range updates properly. Okay, there are some tricks to do it, but essentially it doesn't support range updates. Apart from that, there is another function which is called query. So what the query function does is, to the query I give it an index, and it will return the sum of all elements up till the index. So basically it will return the prefix sum, and to use it for arbitrary intervals, the operation must be commutative. So unlike the previous operations that I talked about, unlike the previous structures that I talked about, here the commutativity is necessary. It wasn't necessary in prefix sum or in the sparse table or segment tree, but here commutativity is very necessary. If the operation is not commutative, Fenwick tree won't work. So there is the query time is log per query, and the update is also log per update. So one thing you would think is that segment tree also performs these operations, and it is it doesn't require invertible operations. I mean, you can see that here you need the operation to be invertible, but in segment tree you don't need the operation to be invertible. Also, in segment tree, commutativity is not required. So why would anyone ever use Fenwick tree if segment tree is better in every way? So the main reason is that, and also in segment tree and Fenwick tree, the cost is also the same. That is log per update and log per query. So, and range queries are also not available. So the reason Fenwick tree is sometimes used over segment tree is that segment tree is very fast. Like actually, I'm gonna write it in bold. So this is very fast. Now, maybe some of you are thinking, if it's log n and segment tree is also log n, then what does very fast means? So by very fast, I mean the constant factor of Fenwick tree is much smaller than the segment tree, and especially if you're using lazy propagation, then the segment tree is very slow because the constant factor is very high. But usually it can be used for ranges like 10 to power 6. It can be easily used. It will run in less than 1 second. But if you need something faster than that, then Fenwick tree is helpful. So I think that is the end of this session. If you have any doubts, please write it on the live chat so I can answer them, or we can end this session here.